And today, we're lucky to have Brent Nannenga joining us from Arizona State. We're going to be talking about microelectron diffraction methodology and application. Brent, are you there?
I am there.
Yeah, if you could swap screens here.
Yep. Let me get it set up here. All right. Can you see that?
If you, yep, looks good.
Okay.
So if you have questions, you can send them to either you can send them by chat, and we can hold on to them. And then at the end, we'll also have some time to unmute folks and let them ask questions directly. So you can save your questions to the end, and you'll be able to ask Brent yourself. So with that, go ahead.
All right. Great. Thank you. So today I'm going to talk about the technique of microcrystal electron diffraction, or MicroED. We're going to go over sort of the methodology, how the technique works, and then some quick examples of different samples that you can use this technique on that have come about recently. So I'm from Arizona State University, and in my lab we have sort of a broad range of interests, protein structure and engineering, and how those areas intersect. Today, mostly I'm going to be talking about this section in the top left, MicroED methods and applications, which happens to be the title of the talk. So this is a project, MicroED, that I started working on when I was a postdoc with Tamir Gonen, and since starting my own lab, I've continued to kind of work in this area. So just to orient everybody, MicroED is a method within sort of the broader cryo-EM field. You've got things like imaging-based techniques like electron tomography, single particle reconstruction, which most people are familiar with. And then you've got crystal-based methods where you'd lump in 2D electron crystallography. That's where you're looking at two-dimensional crystals, generally of membrane proteins, where you collect either diffraction patterns or images from those. And then the more recently developed technique of MicroED, where we're going to look at thin three-dimensional microcrystals and collect diffraction data from these using a cryo-electron microscope. So why would we need to use electron diffraction when you can use X-ray diffraction? X-ray crystallography, of course, has been wildly successful for structural biology. Solved many structures to very high resolutions. So what's the problem with this? Well, when you've got crystals that look like the picture here, these really large, beautiful crystals, there really isn't much of a problem. You can collect diffraction data from these and solve the structure, but as happens with many samples that many crystallographers are familiar with, is sometimes you get this, which are really tiny crystals that are too small for sort of conventional X-ray crystallography methods. So what do you do here? Well, obviously you can try to optimize and try to grow these crystals larger, which is something that that most people do. But sometimes large crystals can be very difficult to grow, very time-consuming, and sometimes they may never grow larger. So there's a need in crystallography to develop new methods that try to solve structures from these tiny crystals. And the approach we use is we use electron diffraction instead of X-rays. Why electrons? Well, electrons interact with matter much stronger and deposit a lot less energy compared to X-rays. So that allows you to collect data from very tiny crystals, crystals that are orders of magnitude smaller than what you can do with X-ray crystallography. So how do we collect diffraction data? Well, if you're in cryo-EM, this should look familiar. So this is just, this slide is just to highlight the fact that you can use the same instrument, the cryo-electron microscope, to collect both images and diffraction. So when we're talking about diffraction data, we're using the same type of microscope you'd use for imaging. You would just swap modes. So if you're looking at an FEI or a Thermo Fisher microscope, there's a button that says diffraction mode, and you push that, and what it does is it projects the diffraction pattern onto the detector rather than the image plane. And so you can collect diffraction patterns and sort of swap back and forth from imaging mode to diffraction mode, which is actually very useful when we're talking about collecting MicroED data. Back to sort of this comparison between X-ray diffraction and electron diffraction. This is more for the crowd here who might be X-ray crystallographers, who might be familiar with X-ray diffraction, just to highlight some of the key differences that make MicroED unique compared to X-ray diffraction, or one of them that makes the data processing unique. And that's the fact that when you're collecting data with X-ray diffraction, if you look at this figure here, we sort of have a cartoon up here at the top. I don't know if you can see my pointer here on the screen. This here is representing the reciprocal lattice. So you can imagine that you've got maybe H going this way, K coming out of the screen at you, and then L kind of coming up in these steps right here. Now with X-ray diffraction, your wavelength is about 1 angstrom, 1.54 if you're using like a home source. That means that the EVOL sphere, which is drawn here in blue, that's going to show you which reciprocal lattice points are going to show up in your diffraction pattern is where this EVOL sphere intersects these points. And so for X-ray diffraction, it's a sphere, so it's curved. And so you get a diffraction pattern kind of on the bottom, which is a lysosome diffraction pattern. And you can see rings and lunes. These represent this sort of different, this would be H and K, and then you'd have L would be in these subsequent rings. So you get three-dimensional information about the lattice from a single diffraction pattern. Now the difference with electron diffraction is, if you look at the relativistic wavelength of an electron, example here is a 200 keV microscope, you'd have a much, much smaller wavelength, which means your EVOL sphere, which is just 1 over the wavelength, is much, much larger. So essentially it's flat. And so what that means is you get a lot of information right here about the H and K, but you don't get information about L. You don't get three-dimensional information about the lattice. And you can see here, this is an electron diffraction pattern of lysozyme. So same crystal form, just in electron microscope, and you can see the diffraction pattern is relatively flat compared to the rings and lunes you see in X-ray diffraction. And what this means is you can't index a crystal in electron diffraction by a single pattern. And this was kind of a bottleneck for a while with using electron diffraction until we kind of started developing MicroED. I just want to zoom in here because this pattern is really, really nice. You can actually see this happens to be on the 001 plane of lysozyme. So you look here, you can actually see the A star and B star axes, and you can even see the systematic abscisses, and you can see the symmetry in this pattern. So it's a really beautiful pattern, but again, you can't index this unless you already know what the unit cell parameters of this crystal were. So the question we had was like, okay, well, you can't collect data from a single crystal. Well, what happens if you can collect data at a very, very low dose and maybe collect multiple diffraction patterns from a single crystal? You could then build up this reciprocal space by collecting multiple diffraction patterns at known or at known angles relative to each other, and you could potentially index the crystal. And so that would require collecting diffraction patterns at extremely low doses. And so you can see here, normally, you're collecting data around 5 to 10, 20 electrons per angstrom squared for biological samples. So if you're consider this somewhat of a limit to how much dose you can give your sample, and you need to collect a whole range of images from one crystal, that means you have to collect data at significantly lower doses than this 5 to 20 electrons per angstrom squared. And so you can see here in this diffraction pattern, with only a dose of 0.05 electrons per angstrom squared, you can see diffraction spots from this lysozyme crystal to beyond 2 angstroms. So you can, in fact, collect data at very, very, very low doses and then collect multiple diffraction patterns from that same crystal. So really quickly, what would this look like? Advance the slide here. What would this look like if you're collecting data? So this method of data collection, we call it, for MicroED, we call it continuous rotation data collection. There's going to be a much nicer video showing how this sort of all comes together in the grand workflow of MicroED. But just to get an idea of how this works and how this overcomes the barrier of being able to index your crystal, you can imagine here's the microscope. So this little box up here, this would be the electron source. You've got your crystal on a grid. You've got your detector down here. Now you tilt your crystal, and if you were to take a single diffraction pattern, you would basically sample this area of reciprocal space. So again, not enough information to actually index this crystal, get the unit cell parameters, and get the orientation. However, if you collect this crystal, you collect multiple frames as the crystal rotates in the beam, you can sort of fill up and sample a three-dimensional volume in reciprocal space here. And so instead of getting a single diffraction pattern like you shown on the bottom, what you'd end up with is a series of movies that movie doesn't look like it's playing here. let me see if I can start it up again. There we go. Where you can see each frame, the crystals sort of marching through reciprocal space. And because you know how fast you're rotating, you know how each frame is related to each other, and you can build up reciprocal space. Kind of the same way that an X-ray diffraction pattern, all the information you get from a single pattern, now you can build that up with multiple patterns from electron diffraction. This was sort of the big key to making MicroED work. I was collecting multiple diffraction patterns. So what does the MicroED workflow look like? Well, the first step, so we're going to march through how would you conduct the MicroED experiment in this slide. And then again, there's going to be a much nicer video kind of showing all these steps in detail. But the first step obviously is identifying microcrystals. And there's a lot of ways you can identify microcrystals. In this picture here, you can see there's a drop that you get from sort of a sitting or hanging drop crystallization experiment. And you'd see, okay, you see large crystals, but you also see kind of these little tiny shower of little dots down here. And so in this case, these are little tiny crystals. So generally what we'd see here is you'd see, okay, you see big crystals, but you also see a lot of little crystals. And so what you do is you take a sample like this and you deposit it onto a wholly carbon grid. So similar types of grids you'd use for single particle cryo-EM, if you're familiar with that technique. You deposit the sample, the crystals onto that grid, and then you would need to blot that grid away, just like in single particle cryo-EM. You need to blot all the excess liquid away, leaving just the crystals and potentially a thin layer of solvent around the crystals on the grid. The reason for this is because X-rays interact with matter so strongly, which is the big property that allows us to collect diffraction data in the first place, it also means that if your samples are too thick, you can't see through the grid and identify where your crystals are, and the beam will be absorbed. You can't even collect electron diffraction data. So just like single particle, if you're familiar with that, if your ice is too thick, you just see nothing, you see black. It's the same thing with crystals. If your grid's too thick, you just see nothing, you see black. And so you have to blot this away. And we do this the same way you do it with single particle, is you put it into a plunge freezing device, or either a manual homemade one or something like a VitraBot, and you would blot it with filter paper, remove the excess liquid, and then immediately plunge into liquid ethane and vitrify your sample. Now, at this point, you'd leave your sample under liquid nitrogen to keep it cold, and then you'd load it into a cryo-electron microscope, and you initially screen the grid. And you'd see something like this. You can see in this case, there's all the grid squares at relatively low mag, and you can see there's crystals all over the grid. So you identify these squares that look promising. You go up in magnification. Again, all this is at very, very low dose, and you'd start to screen and identify crystals. You see here, here's a nice little crystal right here. I use this picture because you can see the nice sharp edges of the lysozyme crystal here. It is a bit misleading because the crystal happens to be in the hole, and that's not necessarily a requirement. Most of the crystals we shoot are actually not over the hole, they're on the carbon, and that's fine. But you can see here, this is a little tiny crystal. It's about 1 micron by 2 micron, maybe 200, 300 nanometers thick. And you're gonna collect data from this crystal. So you put in selected area aperture to sort of limit where you're going to collect your data from. You switch the microscope into exposure mode, and then you're going to expose and collect an initial diffraction pattern down here. And in this case, you'd see beautiful diffraction spots that extend to high resolution. So you'd set the microscope up to collect a full data set where you, similar to the slide I showed before, where you pre-tilt the grid, you start the stage rotating, you collect, and then you collect data with a high-speed detector that's sort of reading out in sort of a movie mode to collect multiple frames with no readout time between the frames, because the stage is going to be continuously rotating. So any dead time while the detector reads out, you're going to be missing data. So you need a high-speed, high-quality detector for this. And I can answer any questions later about what kind of detectors those might be. Once you get these data, you convert them into file formats that data processing programs can recognize. And actually, from this point, if you're an X-ray crystallographer, the workflow looks very familiar. You just process the data in relatively standard crystallographic processing programs, things like XDS or MOSFilm. Use the CCP4 suite to phase the data and refine the data, or use Phoenix. Whatever your preferred program is, you can use it on these data because it looks like X-ray data. It just came from an electron microscope. And so you can solve the structure that way. Now again, I promised a much nicer video. It might play some music, so I apologize, but this is a video that Thermo Fisher put together, sort of showing the MicroED workflow. So you can see here, here's crystals on the grid. Right now they're in solution, and then you're gonna vitrify this. Let's see if I can turn off the music there. There you go. So you're gonna vitrify that, and those are gonna be loaded into an electron microscope. In this case, this would be a side entry holder, but you could use a Krios with an autoloader too. You're gonna tilt the grid, and you're gonna collect diffraction data as the stage rotates. And so you can see in the bottom, there's sort of a roll of movie frames coming out as the stage is rotated. So each frame represents a wedge of reciprocals, a wedge of data you've collected that has sampled a bit of reciprocal space. Now you take all those data, you have a whole movie now. Each diffraction pattern, after you would index it and get the unit cell parameters of orientation, you'd then integrate all of those reflections, and you basically end up with a list of Miller indices, HKLs, and intensities, and all the other statistics you normally get by the data processing programs. That would then be merged together in a full data set that would span, in this case, most 100% completeness for reciprocal space. And so you'd have all the intensities and all your HKs and Ls in a final data set. Now you could take that final data set, and like I said before, just put it through regular crystallographic processing programs to solve a structure. Here's an example of a very nice structure that was solved using MicroED. And so you can see the maps and the data look very similar to what you would see from your X-ray crystallography experiment. Just for the crystallographers, we have another structure here with some more statistics. For those who are familiar with these statistics and want to take a look at them, if you look at things like multiplicity, completeness, CC half, all these sort of things, you can see that they're very high quality and very similar to what you'd expect for X-ray crystallography. So that's a brief rundown on the methodology, how you collect data. I'm going to quickly talk about what led to this. So the first report that came out of from MicroED was in 2013. We solved lysozyme with about 2.9 angstroms or so. That came out in 2013, and immediately we started improving the methods to collect data. And in 2014, a few months later, from the same batch of crystals, because we improved the way we collected data and because we improved the way we processed data, those same crystals, now we solve the 2.5 angstrom structure. If you fast forward about 3 years later, this lysozyme now, I believe, is 1.8 angstroms. It's the highest resolution structure for lysozyme by MicroED. So you can see it's a rapidly advancing field, but also one where methods development is still critical. And it seems like every couple months, a new method, someone's pushing the boundaries. So the point for this is to highlight that it's a great technique, and you'll see in the examples that show up later, you can solve great structures, but also there's a lot of room for continued development and to stay tuned because things continue to get better almost every month, it seems. So what can you do with MicroED? What are the applications? Well, you can obviously do proteins. We already saw some proteins that I used as an example in the last slide. Membrane proteins, there's been a few membrane proteins that have been solved by MicroED, which is a really exciting area because membrane proteins are difficult to work with and often form small crystals. So it's an exciting application for MicroED. Peptides have been very successful for MicroED, solving the structure of different peptides that only grow small crystals. Recently, a lot of excitement has come out from the organic chemistry community about using MicroED for small molecules. And honestly, this is a lot of what I am doing currently, is using small molecules and helping people solve structures of small molecules. I'll highlight an example of that. Natural products, MicroED is really great for natural products research because you only need very, very little, small amounts of material. And oftentimes, there'll actually be crystals in the raw, unprocessed material straight from synthesis. So you don't need grams of material. You can get it from very, very tiny amounts. So natural products is an exciting area of MicroED research. And then material science. There's some applications for material science, and I'll talk about one towards the end here. So the first example, this is kind of a joint sort of section where we're going to talk about an example of how you solve proteins by MicroED, but also sort of where some of the method development is going in MicroED. And that's this particular project that's going on in our lab in collaboration with Wei Liu here at Arizona State, and also Tamir Gonen, my old postdoc advisor who's now at UCLA. And that's to try to extend MicroED to be able to look at crystals that are grown in lipidic cubic phase. If you're not familiar with lipidic cubic phase, it's a great tool for membrane protein crystallography. It helps crystals crystallize in a lipid environment. And one of the big targets that has been used with LCP has been GPCRs, which are a very important class of proteins. As you can see here, there's this LCP matrix. So you've got this sort of continuous bilayer where the proteins can diffuse and crystallize within the LCP matrix. And you get something that looks like this. These are cholesterol crystals, so not a membrane protein, but you can get these crystals growing inside the LCP matrix, which you can see is right here. The problem is with proteins, with membrane proteins, not surprisingly, is you don't get these big, beautiful crystals like you can see with cholesterol. Oftentimes you get really, really tiny crystals. And so this, we felt, is a perfect application for MicroED. You've got a problem where you only get tiny microcrystals. Well, that's what MicroED does. So it seems sort of obvious to go for this. But what makes this difficult? Well, what makes this difficult is the properties of LCP are very hard to work with for MicroED for a couple reasons. One is it's very, very viscous. If you've ever worked with LCP before, you know it has sort of the consistency of toothpaste. Now, with cryo-EM, you have to blot your sample away once you put it on the grid. So something that's the consistency of toothpaste does not blot very well. So that's one problem. The other problem is you can't simply just dilute it away, because LCP is one phase of this sort of solution lipid phase diagram. And so if you start diluting, you don't necessarily just remove the LCP, but you can start to flip phases, which may be actually more viscous or may cause your crystals to crash out. So you have to really play with this phase diagram in sort of make educated decisions about how you're going to work with the LCP so you don't make an even worse phase in LCP. So, sorry, there's another slide there. So our approach to try to handle LCP, because we need to get rid of the excess material, is to look at different sample preparation strategies for how to modify the behavior of the LCP. We came up with two methods. One is to use additives to reduce the viscosity. So you add different things. As you can see here, this untreated LCP, it's hard to see this picture, but basically on the filter paper, it just stays a big blob. It doesn't do anything. However, when you treat it, for example, with this silicon oil, you can see that this LCP, once you put on the filter paper, blots away. The second method is to enzymatically digest the LCP matrix. So you add lipase directly to the LCP, which digests the monoolein, which makes up the LCP matrix, into a fatty acid, a glycerol phase, in which case you can just remove the crystals, which are on the more water-soluble side, and deposit them and blot them on a grid like normal. So we treated LCP with method 1 with a variety of different types of additives, and method 2 with a variety of different ways of handling the lipase. And eventually, we found that the compound MPD, which is a common sort of crystallization reagent that most crystallography labs would have, is a great way to sort of cut the viscosity to LCP while keeping the crystals happy in the LCP. And we use the model protein, proteinase K. So we basically grew small proteinase K crystals and then mixed them with the LCP and then saw if we could extract them and solve the structure. And with both methods, both method 1 and method 2, which is the lipase, we were able to solve structures of proteinase K at about 2 angstroms. So the technique works. Currently, right now, we're working on extending this to more exciting samples in proteinase K, and so this is requiring subtle modifications of this method, but it's one area that we're actively developing and pushing forward to hopefully bring LCP crystallography into the MicroED area as well. A second quick story that I have here is, so this is going to be MicroED for the analysis of organic compounds. This is a fun story. So this story is not exciting because the compound itself was exciting or we learned anything new. in terms of new science. But what was exciting was just the speed that we're able to do this project. And I wouldn't even call it a project, actually. It was just something we did for fun. So the background of the story, as you see here in the top, this is the molecule that a collaborator of mine down the hall was trying to make. And they were trying to make it enzymatically. And see, it's an unnatural amino acid. It looks like tyrosine, but it's got extra hydroxyl group. They synthesized this. They got results. They ran the NMR, and the NMR was a bit ambiguous. They didn't seem to show the same structure that they thought they made. And they were kind of going back and forth about how, what's going on. And I was listening to them talk about this, and while we were at lunch, and I said, hey, well, if you've got some of this powder laying around, why don't we just put it on a grid and see if we can solve the structure with MicroED? They said, okay, fine. So after lunch, we went upstairs, dipped the grid in a little bit of the powder, put the grid in a microscope. So and then we looked here and we saw, oh, there's little crystals on the grid. Perfect. We shot this little crystal and saw that it diffracts about 0.6 angstroms. This whole process right here took about, I would say, 5 to 6 minutes to get in the microscope and collect our first diffraction pattern. We collected a few diffraction data sets, and then we ran this through ShellX to get a solution. And we ended up with a solution that looks like this on the right side, where you can see here, this carbon right here, which they expected to sort of join the backbone here to the ring, was missing. And there was an extra carbon up here, which kind of matched their NMR set, but they didn't think that that was possible. Well, the benefit of this is that seeing is believing. So within about an hour, I would say, of getting the sample, we had the structure already, and then we solved the structure, and basically they were convinced that they had made something they did not intend on making. And you can see the actual structure of the map is pretty nice. So why am I bringing this up? Well, this is a really cool story that shows that MicroED can be used not only to solve unique structures and solve new novel things, but it can be used as an analytical tool for making organic compounds. And something that, again, it took a total of an hour to go from putting the powder on the grid to getting a structure that showed them what they had made, and that what they had made was not what they had expected. Another application for small molecule diffraction, and this is an interesting collaboration between my lab and Adam Braunschweig's lab in New York. So they work on organic semiconductors, and they're really interested in these crystals and how they orient in the film, because how they're oriented in thin film sort of dictates how they perform in devices. And so what they would like to see is they would like to see how their compounds are crystallized, what the unit cell structure looks like, and then how that crystal is oriented on the film. Excuse me. And now normally what this entails is they synthesize their compounds, they try to grow large crystals, which may or may not represent the same structure they see in their thin film, and then they collect wide angle scattering data on their thin films and try to correlate the structure they get by X-ray with the thin film data and see if it all makes sense. So in this work, what we did is they basically used the same material they used to make the thin films, and with similar processes, and instead of putting it on their normal substrates, they put them on a TEM grid. And so we're more closely looking at the structure, the crystalline material that would end up in their thin film than if they had grown a larger crystal by X-ray. And so you can see here, this was the first study here, this compound right here, and you can see there's lots of little tiny crystals on the grid. Again, I want to point out how small these are. And these are less than a micron in size, probably less than 100 nanometers thick, so very, very tiny crystals. But these little crystals produce diffraction that looks like this. You can see here, they play the movie. The diffraction patterns are beautiful. We collected data about 0.6 angstroms. We ended up processing it to 0.7 angstroms. So really, really beautiful diffraction data, which then allowed us to solve the structure. And now this structure was already known. This was sort of a test case for this project. And if you look at the parameters that we saw by MicroED and by X-ray, see they're nearly identical in terms of the unit cell we determined. And the resolution for MicroED is actually a little bit better than what they got for X-ray. The big difference here is the crystal size. We have much, much smaller crystals than what they were able to grow for X-ray. And even these crystals were very, very tiny by X-ray standards. So this was exciting. So we went to, and we looked at 2 other samples that had not been solved before, and we're able to solve this, sorry, this is the last example. We were able to sort of look at how this molecule is oriented in the lattice, and then by combining that with wide-angle scattering data, and you can see here matching it with the MicroED data, we're able to determine how it's oriented relative to the substrate. So we did the same workflow with 2 other compounds. These were both unknown compounds. This compound right here, we solved this structure and saw this is how it's oriented. This is what the unit cell looks like. You can see it's held together by these hydrogen bonds in this herringbone pattern. And then by using the wide angle scattering, you can see that it was actually oriented on the substrate with this orientation here. So the substrate's right here, and the crystal sort of lays on top of in the thin film like this. A little bit of a larger protein, or a little bit of a larger organic complex here. You can see the unit cell is much bigger, big for a small molecule, I suppose. But again, we could orient the crystals to the substrate by combining the MicroED data with the wide angle scattering data. So this is a really cool combination of techniques that it's giving this thin film research a new tool for assessing crystal structure and orientation in thin films. The other application here, this is more for material science, where we've been looking at beam sensitive metal organic frameworks. So metal organic frameworks are, excuse me, are very important for separation technologies and things like that, for absorption processes. And understanding their structure is critical to understanding the transport processes through these materials. The problem with them is sometimes it's hard to grow large crystals. You can analyze them with electron microscopy, but they're very, very beam sensitive. So we thought, okay, well, let's try to use one of these metal organic frameworks, MicroED, and see what happens. And sure enough, we get these little tiny crystals on the grid. We can collect electron diffraction data. And because of the high symmetry of these metal organic frameworks, we can determine the structure from a single crystal with 100% completeness. And you can see here's the map. So this is the typical ZIF8 metal organic framework. So you've got these zinc atoms here, and they're sort of with this imidazole linker right here. And you can see the 3-dimensional structure and how it comes together to form these porous structures. Since this is with our collaborator here at ASU, who's an expert in these materials, Jerry Lin, we've also solved 2 or 3 other of their samples, a couple of them unknown, where they synthesized the materials, collected powder X-ray data, and showed that it didn't match anything that they had made in the lab before. And we were able to just go in with MicroED and relatively quickly solve the structure for them. So it's been a really fun collaboration, getting into the material science aspect of things as well. So that was a really quick overview of MicroED and the applications. I'm hoping to further clarify some points in the questions. But just to summarize, so MicroED is a relatively recently developed way of solving structures. And the big benefit is you can use MicroED in a very quick way to solve structures from sub-micron crystals. So crystals that you normally have just not used because they're much too small. A lot of these crystals are even too small for things like free electron lasers. And since the initial implementation, again, when I was a postdoc with Tamir in 2013, methods have been rapidly improving to get better data collection, better data processing, better ways of sample preparation. So the field has really been advancing very quickly. Another huge benefit of MicroED is that it can be performed by many available cryo-TEMs that a lot of universities and research institutions already have. You just need to make sure that you have a sensitive, high-speed detector to collect diffraction data, and you can perform MicroED in most cryo-TEMs. Now Thermo Fisher, I think, is even selling these MicroED packages where if you buy a new cryo-TEM, you can have it equipped with certain software and certain tools to optimize MicroED data collection. And it's very, very nice to have, but the point is you don't necessarily need that. You can do MicroED on a lot of microscopes that you might currently have in your own institution. And another huge benefit of MicroED is that you can use it on several different samples, from proteins to inorganic materials, organic materials, natural products. It works on all these different types of samples, which is an added benefit. I feel, one, because it shows how broad the technique is, but also it helps when you're trying to go over things like funding to buy a new instrument, is that you can bring in the chemistry department, the material science department, the biology department, all these different researchers to get on board with a single technique that can really sort of jumpstart a lot of research projects. So with that, before I take questions, just want to acknowledge a lot of people that helped on this work. My lab here, Guang Hong specifically, did a lot of the data collection of the results that I presented. At Arizona State, Wei Liu, Jerry Lin, Jeremy Mills all helped on the projects I highlighted. UCLA, Tamir Goen, my old postdoc advisor, we still work together quite a bit, and he helped with a lot of the projects and a lot of the data that was shown on this as well. In New York, Adam's lab, which was this organic semiconductor project at Tianxi, who helped collect some data as well, and the funding. And with that, I'll end here and I'll take any questions.
Great. All right, thank you very much. That was fantastic. Anyone who has questions, I think you can raise hand. You could also send me a question by chat, and we can.
In fact, everyone is allowed now to unmute themselves if they want to ask a question.
All right, great. Thank you, Wolfram. So just to kick things off, it seems, from my perspective, from what you've shown, it looks like the primary issue for doing this, just on protein samples is having the thin crystals. Your sample has to be right. Like getting the sample exactly right, would you say that's the primary bottleneck of doing this for biological samples?
Yeah, I mean, just like with pretty much every structural biology technique, sample prep is the critical step. I personally feel it's a step that often gets overlooked. People like the end results more than the beginning steps of actually getting the samples nice. But yeah, every sample is a little bit different. Every sample takes some time to figure out, what is your sample like? How do you get it on the grid? How do you get on the grid and have it still diffract well? In the past, we had to look at things like what kind of, do we need to use cryoprotectants? You can use some low viscosity cryoprotectants and add them to your crystals. The more recent thing that's come out, a lot of this work has come out from Tamir's lab recently, is using cryofibs to mill crystals down, which I think is going to be the future of sample prep for MicroED. I mean, there's still some things that need to be optimized with that, but in that case, it opens the door to more cryoprotectants, for example, maybe less harsh clotting conditions, and then using cryofib. So there's a lot still to be done on optimizing sample prep, but yeah, every sample needs to be, you need to put your time in to figure out what is that sample like.
Yeah, I mean, with the milling, you could actually get the thickness that you would want. I think that. Yeah,
exactly. It's fantastic.
Shihao has asked a question on the chat. Shihao, you might unmute yourself if you want to ask the question live.
Oh, yes. Thank you for the very nice talk. That we all know that electron can pass crystals several times that make reflection intensities are highly dynamical. So how do you tackle these problems of inaccurate intensities while you're dealing with the MicroED data?
Yeah, so referring to sort of dynamic scattering, multiple scattering, so we've seen that it's actually not as significant of a problem as I think a lot of people originally predicted before we started doing this work. I mean, one way that you handle it is you find the thin crystals. You don't shoot through very thick crystals. And honestly, a lot of the time with the very thick crystals, you lose a lot of your electrons to absorption anyway, and so you wouldn't even really collect data from that. But we see that, with the crystals we collect, there is some multiple scattering. I mean, it's not completely gone, but it's relatively minor, and we can still solve structures at very high resolutions very accurately. And there's actually little, not a overwhelming amount of multiple scattering like most people originally thought.
Yeah, I got the point. Okay. Yeah. Can I ask another question? So the natural products are mostly involve a lot of chiral centers. So is determining the absolute structure of this chiral structure are currently challenging for MicroED?
So yes and no. So determining, you can use a lot of the same tricks you use for X-ray. So you could, for example, soak the crystals or crystallized the chiral salt, for example, help get the orientation. But actually, kind of along the lines of your multiple scattering question, theoretically, electron diffraction should be more sensitive to figuring out the absolute hand, and you can do that by modeling the multiple scattering in the crystal. And there was a paper in Science, I forget when, maybe a year back or so, where they've done this. They determined the absolute structure of an organic molecule by modeling the multiple scattering. So again, the multiple scattering is not so significant that it precludes structure determination, but the signal is there, and if you can extract it, you can actually take advantage of it by figuring out the handedness. And so that's what this paper did. I believe is 2019 in Science.
Yeah. Thank you very much.
Another question from Jing Jing. Would you like to unmute yourself and ask your question?
Oh, yes. Thank you for your very nice talk. So I just curious about the determination of the orientation of the crystal on the substrate, because normally we collect data from the PM grid, and it's on top of the carbon film. Probably it will be different with what we have on top of the substrate in reality.
Yeah, so I mean, you have to take that into account. But in this case, I believe they made their substrates on glass substrates, and so these substrates are carbon, so not the same thing. But otherwise, they prepared the samples the same way. So normally they'd have these in solvents, they'd evaporate the solvents away, and they did the same exact thing on the carbon grids. So you're right, if there's any effects of the substrate on sort of the orientation, it might not be correct. But that's not necessarily it's not necessarily the point for MicroED. MicroED is not to get them in the exact orientation that's on the cover slip. The point more is to hopefully get the same crystal form that's on the substrate. So if they don't orient exactly the same way, that's fine. That's actually what we're using the wide angle scattering data for. But if it's the same crystal form, that's what's important, because then we correlate the crystal form we get in MicroED to the crystal to the scattering data, if that makes sense.
Yeah, I understand what you mean, but I mean, for material science, sometimes the orientation of the crystal is very important for the properties.
Yes, and that's why we use the wide angle scattering data to confirm the orientation of the substrate. And the MicroED is used to actually solve the unit cell, the crystal structure.
Oh, you mean that they use another technique to determine to confirm the orientation?
Yeah, so we use the GWAT, grazing incident wide angle scattering, to get the orientation on the substrate, and then use MicroED to solve the structure. And then we take the MicroED data and calculate predicted scattering patterns based on different orientations and match it with the wide angle scattering data from the GWACs.
Okay, thank you. Understand that now. Thank you a lot.
A question from Pete Meyer. Would you like to ask it?
Sure. Brent, thanks. That was a very interesting talk. I guess my question is about the effects of the collecting from the grids with the limited rotation range. And sorry, that was not fully coherent. So with X-ray diffraction data collection, one of the issues is you've got a missing cone when you've got a single axis goniometer.
Right.
And I would have expected that to be worse if you've got a limited rotation range, but from the lysozyme data you showed, it didn't seem like the completeness was an issue. Is that something that's a problem, or am I just having bad intuition?
No, I forgot, I didn't mention one of the important part of that is that data actually, your data sets oftentimes come from merging multiple crystals.
That'll do.
So a single crystal, with the exception of I presented the ZIF molecules, which are cubic, so there it didn't matter. you get 100% completeness with a very narrow wedge of data. But for a lot of crystals, you'll get, say, for lysozyme, most of the crystals actually lay in the same orientation. So you get like 45, 50 degrees of coverage, no matter how much you tilt. But then every once in a while, you'll find a crystal that's laying on the grid slightly differently, and that'll cover a different region of reciprocal space and give you maybe 80%.
Yeah.
And then you merge those two together and you get 99.7%. So yeah, I forgot to mention that. Normally you merge multiple crystals together. For proteins they generally have a little bit higher symmetry than the small molecules is generally not a huge problem. For some of the small molecules, it can get kind of difficult because you get a lot of P1s and P2s with preferred orientation, and you just gotta do your best.
Shake up the grid a little bit, maybe.
Yeah, exactly.
Thank you.
So,
Any other questions?
I have some questions that were sent privately. Should I?
Yeah,
Oh, yeah.
go ahead.
Okay.
I think Hong Yi also has his hand up as well.
Okay, I can wait.
Yeah.
Or,
yeah. Thanks a lot for the very nice talk, Brent. I've got a general question. So going forward, what do you see as the biggest challenge for MicroED? I mean, the method has been out for 7 years, and the many labs has cryo-EMs, and not many people are doing it. So how do you see that? What is the biggest challenge?
well, I think a lot of people are doing it now, especially now that cryo-EMs are becoming more widespread. I think the biggest challenge is just getting people familiar with the technique. It has elements of single particle cryo-EM, so people who are familiar with that are comfortable with things like sample prep and operating the microscope, and it has a lot of elements of X-ray crystallography. So the crystallographers are familiar with, handling the crystals and processing the data, and it's sort of getting people trained in sort of the mixture of those two. I think as more and more people get trained and get familiar with it, I don't think that that's a huge problem. The biggest thing is just mostly just sample prep, figuring out what's the best way to get these crystals on the grid. Again, cryofib is starting to come online, and I really think that's going to be a huge benefit, fib milling crystals down. It's just getting these workflows, ready. A lot of people, compare MicroED with X-ray crystallography, but they have to realize that MicroED is at the place that X-ray crystallography was, several decades ago. Where there's only, been, like I said, it's been 7 years. Well, it took X-ray crystallography quite a while before it became sort of black box, push a couple buttons and get a structure technique that it kind of can be sometimes today. So I think just as more people work on it and more people get excited about it and more technology gets developed, it'll just get that much easier and it's more straightforward to do.
Thanks a lot. Great work.
Thank you. So I can read. So one question I have here is, what's the lower limit on crystal size for proteins, especially membrane proteins? That's a good question. I don't have an actual number answer. The thing is, you need the crystals and they need to be thin, but I don't really think there's a limit on how thin they can be, because you figure, if you get down to a single layer thickness, you could just do 2D crystallography. The big thing is you need enough unit cells to have enough signal. Like I said, off the top of my head, I don't have that number is. So especially if you have a big unit cell, you might need a thin but kind of wide crystal to get enough unit cells to give good scattering. Sorry, I don't have a more definitive answer on that right now. There's another question here. It says, we crystallize a protein with normal size, however, the crystals crack badly when the cover slips are opened. Could MicroED be used on the cracked crystals? Yeah, I mean, there's a really great paper by Tamir and I think Jason, who actually is on, Jason De La Cruz, who actually might be on the call, where they've fragmented large crystals and used them to solve the structure as one way to make crystals small enough for MicroED. So if your crystals sort of naturally crack, those little bits and those little shards might, if they're well ordered, if those little shards are still well ordered, they might be perfect for MicroED. So yeah, so fragmenting larger crystals is one approach for make crystals for MicroED. So it may be worth putting those crystals on a TEM grid and just taking a look and seeing if they're, if there's little bits that are suitable for MicroED.
Great. Any other questions? Samir's got his hand up.
Sorry, can I ask another one?
Sure, go ahead, and then I see Tamir Gonan's got his hand up too.
Oh,
so we can
yes.
come back there. Yep.
I'm curious about the viscosity problem of the LCP phase. So you have tried the two methods and to decrease the viscosity. One is use the silicone oil, another one is the lipase. So how long it will take to decrease the viscosity? For example, a few minutes or a few seconds?
Yes. So I showed the example of silicone oil. We ultimately didn't use silicone oil because the crystals that we had didn't like it. We ended up using MPD, but it was a similar process. For the lipase, and so for that, when you mix in the additives like MPD or things like that, the phase conversion is relatively quick. Now you just mix it a little bit and it's relatively fast. For the lipase, you do have to let it incubate, and I believe we let it incubate for it's more than 12 hours, I think. I'd have to look at the paper again, but that one you have to let it incubate for a while to give the enzyme time to act. But for the additive one, which is honestly the additive one is more successful. That one is relatively quick.
Do you mean the MPD?
Yeah, the MPD. So when I say additives, I'm mostly talking about MPD and some of the other ones we tried. We tried a whole host of additives. MPD ended up being the best. Things like ethylene glycol, PEG 200, low viscosity, things like that. And those you just mix it with you have the LCP in a syringe and you just mix it back and forth until the phase converts.
Thank you. Did you see some phase changing during mixing?
Yes, you see. So basically, you're turning it into a sponge phase instead of the LCP phase, and the trick is to not get it to convert into any other more solid phase. So yeah, that's why you have to control the ratios and control things like that.
Okay, thank you.
Tamir, you should be able to, unmute him.
Hi. I don't really have a question. I just have a comment since the question of dynamical scattering came up twice. And I'd remind you some of the very early experiments you did, Brent, where you have a stationary crystal and the error that we saw from dynamical scattering was about 5% intensities. But once you start rotating the crystal and are continuously rotating it, that essentially mimics precession, which is what is used in material science, for example. And the error dropped down to less than 2%, which is probably coming from detectors more than anything else. And so we deal with the dynamical scattering effect by precessing or continuously rotating the crystals.
Yes, thank you. That's a good point. So one of the other added benefits of the continuous rotation is not just being able to sample reciprocal states better, but it actually allows you to not have to sit on any one orientation for a significant amount of time, and that really drastically reduces the amount of dynamical scattering you see in your data. So again, we actually see, like I think Tamir mentioned, less than 2%. We see very little dynamic scattering in the data. It's enough that if you wanted to take advantage of it for other reasons, you could, but it's not. It's a very, very minor contributor to the data.
Yes, thank you. Great talk. I just have a really naive question. So I'm wondering, that launch project you did with your friend, do you need to freeze the grids because they are not biological samples? They're just like inorganic. It's not like as fragile as protein, right?
Yeah, so that's actually a really good point. I didn't bring it up because I didn't want to sort of confuse and muddle things a little bit, but actually those data were collected at room temperature. So in just a regular standard holder. So sometimes we do see with organic molecules, even though you don't need water, the cryo helps with the radiation damage. So the crystals are still beam sensitive, and the cryo can help with that. These crystals actually were super, super robust. So they could handle room temperature on a standard holder, collected great data. So yeah, that was another reason why it was so quick to do. But in those cases, you don't necessarily even need a cryo holder. But I didn't want to bring that up because then people will be, wait a second, you're not using cryo. You said you're using cryo, but yeah, that's a good point. And we could have used cryo in that project. It just we just used the microscope that was down the hall and didn't bother getting the cryo holder out. We just put it in because we were first just trying to see if there were even crystals on the grid, and we popped in and said, oh great, there's crystals on the grid, let's get the cryo holder going. And we just started collecting data, and then by the time the cryo holder was cooled, we didn't need to collect any more data.
Yeah, thank you. Because one of my friend actually, she has some polymers, but she doesn't know like how those monomers, what's the orientation to be polymerized into this polymer. So yeah, so I'm thinking maybe I can try to use MicroED to help her to.
Yeah, definitely. I mean, the first test is just put the materials on a grid and see if there's crystals there. And if there's crystals there, then go from there.
Yeah. Yeah, because her stuff is actually like multiple crystal. It's not like a single crystal. So I don't know, like, yeah, maybe there are several different combination of different polymers. I don't know. Yeah,
and there's been work by Tamir where they showed that you could put multiple small molecules on a single grid and solve multiple structures from one grid. You could just collect multiple crystals, and those crystals are all they're different compounds, and you could solve the structures from them.
Could you please share that? Which paper, which journal?
This is, Tamir might be able to help me with the reference. I believe it's 2000, it's a small molecule paper where the first time MicroED was sort of shown that it can be used on small molecules. It's in, I think it's in ACS Central Science 2018 or 19, I believe.
So the first small molecule paper that I can remember was from J.P. Abrams, 2016, carbamazepine at room temperature. We did carbamazepine in cryo in 2018. That's a Gallagher-Jones paper. And then later in 2018 was the ACS paper showing 12 different compounds. And there was also a Gruna et al. Paper in 2018. And I can't remember if they did this in cryo or not.
I believe theirs was cryo, but they only did one sample at a time. They did 2 different samples.
Yeah, thank you very much.
Yes, maybe I can comment if it's okay. We also did the zeolite that we had 4 different phases on the grid, and we did it in room temperature as well. So it's possible to separate phase. And I think one of the powerfulness of MicroED is that you can do phase analysis on the grid. And there is a technique called serial crystallography, serial electron crystallography. So we collect one diffraction pattern from one crystal on the grid. So we can go through thousands of crystals per hour and then analyze the phases of them and collect 3D data from them if possible.
Yeah, thank you. Yeah.
No worries.
Ken, you have a question. Okay, Ken wanted to clarify whether we are dealing with precession or rotation in these experiments.
This is rotations. The stage is rotating, the beam is not.
I think that wraps up the questions. We've got 1 o'clock now. We can stick around if people have more questions, if you have time, Brent. But otherwise, we can do the official wrap up, and we can hang out and do a little bit more discussion if people have time and you're available. So thank you very much for a great talk. Thanks for joining us. And for anyone who's still on the call, who's join us next week for our last in the series. And thank you very much.
Thank you.